Good morning, students. In the last session, we have learnt about the nanotechnology as well as nanoparticles. Why we want nanotechnology, what are its pros and cons, as well as what are the challenges we are having in nanotechnology. Because by the nanotechnology, by the technique of or the technology of a nanotechnology, by using this technology, we are going to synthesizing, or we are going to make a use application by using these techniques. So today in this session we will learn about how to synthesize the nanoparticles, because synthesizing of nanoparticles is not an easiest task here. So we are going to have a synthesis by using different techniques. So in today's session we will see the synthesis of nanoparticles. First of all, nanomaterials here, material having unique properties arising from their nanoscale dimensions. So when we are going to make or when we convert the material from huge material, or it may be in terms of a longer material, to the shorter form in terms of nanoparticles, the volume goes on decreasing. The volume goes on decreasing, but the surface goes on increasing here. So that is what we are having. So the smaller nanoparticle will have high strength. How it is? Because the volume ratio goes on decreasing. In the same way, we are going to see the surface of the atoms or surface of the molecules will be having more here. So that is the distribution or the opening of the surfaces of these atoms becomes more here. So the surface to the volume ratio, when we see the surface to the volume ratio, we see that the material is having more surface here. That is, the material with the smaller size or the nanoscale dimensions will have more strength as well as the properties here. So nanomaterial with the fast ion transport are related also to the nanoionics and nanoelectronics. So here we are having a smaller material, that is in terms of nano, but the transformation of the data or transformation of the ions will be here the faster. So nanoscale material can also be used for the bulk application. When we think about the different applications, whatever we use the nanoparticles, by using nanoparticles we are having a different application in terms of medicine or in terms of health. When we talk about the in terms of the for the different applications, we are going to have a bulk application by using these nanomaterials. So nanomaterials are sometimes used in solar cells, which combats the cost of traditional solar silicon cells also. So here by having all these advantages of the nanoparticles in nanotechnology, we have to know how to synthesize the nanomaterials or the nanoparticles here. So here we are having two approaches for the synthesis of the nanoparticles. The first one is the bottom-up approach, and the second one is the top-down approach here. So bottom-up approach is nothing but that is from the smaller particles, from the smaller, that is from the atomic or from the molecules, we are going to make the nanoparticles by using a small that is in terms of the micro level. From the micro level we are going to make the nano level. So that is what we are having in the bottom-up approach. When we go for the top-down approach, from the macro level, that is from the huge material, we are going to make smaller nanoparticles. That is what we are having. So huge material, from the huge material we are going to make a smaller particles here. So for example we are having we are having the we are having an example of the sculpture. That is what we are having. So when we talk about the making a sculpture by the carving here, that is the sculpture which is made by the huge rock by the carving process. So by the sculpture, what he will do is he makes the big statues or the sculptures which are made from the huge rock. The bigger rocks which are converted into the statues or the sculpture here. So that is nothing but from the huge material we are going to convert it for the smaller particles here. That is what we call it as top-down approach here. So most of the cases we use the bottom-up approach for the synthesis of nanomaterials. That is, here we are having one of the figure. You can see here what exactly the top-down as well as bottom-up approach. So first we will see the top-down process, because we are having from the top. When we see from the top, we are having the bulk material. So the bulk material in this figure, you can see from the bulk material. We are going to convert the bulk material in terms of the powder form as well as in terms of the nanoparticle here. That is what we are having. So top-down approach is nothing but from the huge bulk material we are going to convert it to the powder form, and that powder which we are going to convert it to the nanoparticles. When we talk about the bottom-up approach, that is from the bottom. From the bottom, if we see from the atomic level or in terms of molecules, the molecules which are converted to the clusters, and these clusters which are converted to the nanoparticles. So from the micro level, we are going to convert it to the nano level. So micro scale to the nano scale we are going to convert in the bottom up approach. And when we talk about the top down approach, we are going to see from macro level we are going to convert it to the nanoparticle here. So that is what the technique we are having in the top down approach and the bottom up approach here. So first we will see what to mean by the bottom up approach. So this approach includes the miniaturization of material components up to the atomic level, with further self-assembly process leading to the formation here. So this seeks to arrange smaller components into more complex assemblies. That is, the smaller atoms or molecules which are joined together, which are self-assembled together to form a huge complex assemblies here. So using of chemical or physical forces operating at the nanoscale to assemble basic unit into larger structure here. So during the self-assembly, the physical forces operating at a nanoscale are used to combine basic units into larger stable structures here. So we are having an example of a quantum dot, that is formation during epitaxial growth and formation of nanoparticles from colloidal dispersions. So from the colloidal dispersions we are going to make nanoparticles or the nanomaterials. So these nanomaterials which are synthesized by assembling the atoms or molecules together. When we instead of taking material away to make structures, the bottom-up approach selectively adds. Here we are going to have an adding of atom to the atom or molecule to the molecule to create the structures here. So for example, we are having the chemical vapor deposition, or it may be the plasma etching. So these techniques which that is the chemical vapor deposition or wet chemical vapor deposition, sol-gel techniques, gas condensation techniques, all these are nothing but the vapor deposition techniques. All these techniques are nothing but the bottom-up approach here. So for example, we are having the indium gallium arsenide So quantum dots, what I have told, can be formed by growing thin layers of the indium gallium arsenide material. So formation of carbon nanotubes. So the best example, by using the bottom-up approach, we can manufacture the carbon nanotubes, that is a single-walled nanotubes as well as multi-walled carbon nanotubes can be manufactured. So in the last class session we have seen that what to mean by these carbon nanotubes as well as single-walled carbon nanotubes and multi-walled carbon nanotubes. We have seen the same carbon nanotubes can be made by using the bottom-up approach here. Next we'll go for the top-down approach. So what exactly this top-down approach? This is to create smaller devices by using larger ones to direct their assembly. That is, from the huge bulk material, we are going to convert this huge bulk material to the nanomaterial here. So the common top-down approach to fabrication involves lithography patterning techniques using short wavelength optical sources. So from these short wavelength optical sources, that is in lithography technique, we can make the pattern. By using the patterning techniques, we can go for this example for top-down approach here. So uses that is the, in this we are going to have a macroscopic materials. Macroscopic, that is a huge material that can be converted into the nanostructured and extremely controlled in the controlled process here. So that is, for example, we are having ball milling technique, or it may be the etching through the mask, or else it is an application of severe plastic deformation. So when we talk about the plastic deformation, that is the when a load is applied to the materials, it goes for plastic deformation. So that is, the material goes on changing its deformation. So huge bulk material, when we go for hammering the material, it converts into the smaller particles here. So that is nothing but the top-down approach here. So nanomaterials which are synthesized by breaking down bulk solid into nano size. So top-down processing have been and will be the dominant process in semiconductor manufacturing. So in semiconductor manufacturing, we are going to see the top-down approach here. So ball milling, or it may be the sol gel technique or lithography technique, which all these are nothing but the top-down approach here. So I explained this figure already. So we are having the different methods. So how to convert? We have seen the approaches, that is bottom-up approach or top-down approach. So today, in today's session, we will see the different methods, because when we talk about the bottom-up approach as well as top-down approach, we are having the different methods or the techniques by which by these approaches we can go for converting the material to the nanomaterials here. So we are having the three methods for the synthesis, that is by the physical, chemical and biological techniques we are having. So here, physical methods of synthesis. So physical method is by we are having the two methods. When we talk about the physical methods, that is by using the mechanical and vapor. So in mechanical, we are going to have a high energy ball milling and melt mixing. These are the two techniques which we are going to see in the mechanical methods. And when we talk about the vapor, in vapor we are going to have a physical vapor deposition, laser ablation, sputter deposition, electric arc deposition, ion implantation. These are the methods or the techniques which we are going to see in the vapors. So here, for our syllabus, we are going to have a mechanical by high energy ball milling, as well as when we talk about the vapor, we are having the physical vapor deposition, chemical vapor deposition. We are having the gas condensation techniques, as well as wet chemical deposition. When we talk about the chemical method, in chemical method we are having wet chemical methods that is the sol gel technique, as well as gas condensation techniques we are going to see here. So first we will see about the we are having a high energy ball milling. So here simplest method of making a nanoparticle in the form of powder form. So by the mechanical method, that is various types of mills we are going to have. When we talk about the ball milling we are having various types, that is by planetary, or by the vibratory, or by the rod, or by the tumbler methods. So we are having different types of the mill. By using the different type of the ball milling technique, we go for the conversion of bulk material to the nanoparticles here. So ball milling, when we talk about the ball milling, this is the figure which indicates the ball milling technique here. So we are having a refractory or a steel balls, in between the steel, in between these balls, we are going to have a bulk material. So when the bulk material is passed in between these two steel balls which are rotating at high speed, when it comes in contact with this material, the material, due to the impact force of both the steel balls, by this impact force with high speed, the material, bulk material, which converts to the nanomaterial here. So these nanomaterial will be taken in the outside the chamber here. So this technique which we are going to see at the that is at the room temperature we are going to have. So this is the machine, what we call it as a ball milling machine. So you can see the second figure here. So it is having the impeller we are having, that is the rotating impeller. In the same way we are having a steel ball bearings we are going to see here, and we are going to have a gas seal. So here we are going to have a water cooled stationary tank also we are having. So when the ball milling starts to rotate here with high velocity, with high speed, the inner, that is the steel balls, goes on rotating here. So you can see the third figure here, that is the circle what we are going to see. These are nothing but the rotary, the tank or rotary tank what we are having. In this we are going to see the steel balls. So when it starts rotating, the steel balls also start rotating here with high speed. So due to the collision between the material and with the steel ball, due to the impact force of these steel balls with the material, bulk material, the material will convert to the nanoparticle here. So due to the collision between one steel ball with the other steel, in between this we are going to have a material here. So the metal material what we are going to have, this will come in contact between the steel balls here. So with the timing, based on the timing, if you go for the 5 hours, 10 hours, 15 hours, then the material goes for converting to the nanoparticle. So first the bulk material which converts to the macro, next it goes to the micro, micro to the nano. So the particle size in terms of microns or in terms of the nanomaterial, when we talk about the nanomaterial, if you want to make a bulk material to the nanoparticle, then it takes a huge time, from 5 hours, 10 hours, 15 hours, like this. Based on the timing, the material we can see in terms of the nanoparticles here. So here we are going to have the which is consisted of the container filled with hardened steel or a tungsten carbide balls. So here when we talk about the stainless steel balls, so in some cases we are going to see the tungsten carbide balls also. So why it is? Because when we are going to have a high strength materials, when we are having a wear resistance materials, so at that time steel balls does not work here. So at that time we want the tungsten carbide balls here. So because of that we are going to see the hardened steel balls, or it may be the tungsten carbide balls. So the material of interest is fed as a flux here, that is the huge material which is converted in terms of the macro stage, that is in terms of a flux, it is converted and then it is poured into the ball milling the machine here. So it is 2:1 mass ratio of balls to material, 2:1 material, where that is in terms of a macro. Huge bulk material cannot be poured into the chamber here, so because of that we convert this to the macro and then it is poured into the chamber for the ball milling here, that is in terms of a 2:1. So the container is filled with air or inert gas. So the container which is filled with air or inert gas, containers are rotated at high speed around the central axis. Material is forced to the walls and pressed against the balls here. So this material, when it comes in contact between the balls, due to the impact forces and due to the friction of the one to another, the material which comes in between the balls will convert to the nanoparticles here. And the control speed of rotation and duration of milling grind material to fine powder. So some materials like the cobalt, or it may be the tungsten, aluminum, iron, that is the AGFE, etc. are made nano crystalline using the ball milling. So these all can be made in terms of a nanoparticle by using this ball milling process. So in this process we are going to use inert gas. Why we are going to use the inert gas is because the inert gas which carries, because when we have an inert gas in this chamber, the material which converts to the nanoparticles, these nanoparticles will be carried. The nanoparticles will be carried by the inert gas to the one of the place here. So that is the material which is converted to the nanoparticle. These nanoparticles will be carried by the inert gas and it will be dumped in one of the chamber here. From that chamber, the material will be taken out. That is one chamber to the another chamber. The nanoparticle material has to be transferred. So the transferring is done by the inert gas here. So inert gas with the high vacuum, with the high pressure, the material comes to the another chamber here, and from there by the vibrator or by the what we call it as by using the other methods, we go for taking out of the nanoparticle from the chamber here. So that is what the technique we are having in the ball milling process here. So this is the figure what I have explained earlier. So here the ball milling process which depends upon some of the factors here. So the factors are nothing but here the rotational speed of the ball. So based on the rotational speed of the ball, the material, that is conversion of the macro to the nano material, it depends upon the rotational speed of the ball here. The size of the ball. So if we are going to have the different size of the balls, so then the material material does not convert to the uniformity of the nanoparticles. So because of this, the size of the ball should be similar here. So when we are having a similar size of the balls, that is the tungsten carbide or it may be the hardened steel, whichever it may be, if we are having the similar sizes, then the uniformity of the nanoparticle, that is in terms of homogeneous materials, we are going to get that homogeneous nanoparticle materials are being generated here. Otherwise the material will become heterogeneous here when the sizes of the balls goes on varying here. In the same way, number of ball milling time, that is the timing, based on the timing, I have already told this, based on the timing, that is for 5 hours, 10 hours and 15 minutes, the size of the nanoparticles goes on varying here. And in the same way, the ratio of ball to the powder, that is what we have told, that is 2:1. So that is nothing but based on the ball size and based on the macro material, that is the raw material what we are going to have, that is the ratio of ball to the powder mass milling medium or the atmosphere, that has to be maintained in terms of 2:1 ratio here. In some cases we are going to have a cryogenic liquid can be used. to increase the brittleness of the product. Here, that is, when we use the cryogenic, we should have to follow some of the steps to prevent oxidation during the milling process here. So when we add the cryogenic liquid, we should have the care should be taken, that is to prevent the oxidation during the milling process here. And this ball milling process, the selection of the ball milling process influence the type of material obtained, that is the harder material balls. Synthesis of the softer material, that is the alpha alumina and zirconia, are widely used ball materials, as well as tungsten carbide or high speed steel. Based on the material, that is the grinding ratio, that is grinding of the material, or the size of the particle which we want, that is based on that we are going to use a different type of the materials of the ball here. So what are the advantages of this ball milling? So when we talk about the advantages, when we learn about the different techniques, one will be having the advantage as well as disadvantage here. So in the same way, we are having the advantage here, that is the scaling can be achieved up to the tonnage quantity of material for wider application. That is, we can have a mass production. When we talk about the ball milling here. But the disadvantage, that is the contamination of the milling media. So the contamination, because we are going to have a tungsten carbide, or we are going to have a different type of the material balls here. So if we are going to have a high speed, or somewhere if it takes an oxidation due to the high speed, then the material will have a chemical reaction here. So that is nothing but the contamination we are going to see. So for example, when we talk about the non-metal oxides required an inert medium. When we talk about the non-metals, metal oxides requires an inert medium and vacuum or glow box to use powder particles. So the milling process is restrictive at that time. So the milling, that is ball milling, can be restricted to some of the materials here. So non-metal oxides cannot be done in this case by using ball milling process here. So based on this, that is the metal oxides can be done by using this ball milling. So this is some of the disadvantages with respect to the ball milling. But when we want to have a mass production in terms of the nanoparticle, we prefer the ball milling process. So this is the session. In this session, we have learned about the different type or the approaches by which we can synthesize the nanoparticle, and the methods which we are going to have in the bottom-up approach as well as top-down approach we have seen, as well as in today's session we have learned about the top-down approach. So in top-down approach, we are going to have a ball milling process, high-speed ball milling process for the production of high quantity in terms of high productivity. With a precise quantity size, we can produce or synthesize the nanomaterials. So this was the session which we have learned these topics. In my next session, I am going to have different techniques by the bottom-up approach. By the bottom-up approach, we can go for the synthesis of nanoparticle by using the bottom-up approach by different techniques. So in my next session, I am going to have these different type of the techniques. Thank you, students.